Alright, so in this section we're going to talk a little bit about concavity and then get on to the second derivative test, which is a test for relative extrema. Alright, so what we're going to start with is a regular function, such as like a cubic function. Didn't make mine very symmetric actually, so we made a little estimation of one. So for this function, we have a piece that's increasing, then it has a horizontal piece where the derivative is equal to 0 here at -2. And then it decreases for a little while. We'll talk about this point here in a second. And then it stops decreasing and starts increasing here after 1. So the first derivative test tells us is there's a local maximum here because the derivative goes from, well, the function goes from increasing to decreasing. And a local minimum here because the function goes from decreasing to increasing. So if we were to try to make the first derivative of this, we would take our two little horizontal lines and realize that's where our slope would be 0. So over here, I put my two zeros at -2 and +1. Now, to the left of -2, the function is increasing, so that means my derivative has to be positive. Between -2 and +1, the function is decreasing, so my derivative has to be negative between these points. And then after 1, it should be increasing, so after 1, it should be positive. Now, if you think of this as being an x cubed graph, so it's pretty easy to see that the derivative should look kind of like an x squared graph, and the derivative of that should be x to the first. Now, I know I made some terms max and min, so there has to be more to this graph, but derivative of the cubic is a quadratic. Derivative of a quadratic is a linear equation. So it all matches up. Now, there's a point right here. When I look at the derivative, I can kind of tell that there's a relative minimum of this derivative. And what that point is really, it's really this point right here. And it's where the graph changes from being concave down to being concave up. Think about how, like, when you talk about a parabola, whether it's pointing up or pointing down. At some point, when you've got something concave down then concave up, or concave up and then concave down, there's a point somewhere in the middle where that concavity changes. Now, a couple things about concavity. Straight line has no concavity. It doesn't have a positive concavity or a negative concavity. You think of somebody sitting inside the cave. I don't know if you've ever heard that for concave and convex. These guys are in the little caves. This one's concave down, this guy's concave up, but they're in. It's kind of needed for concavity. There needs to be some sort of curve to this. So this point where the concavity changes from concave down to concave up is called a point of inflection. So the point of inflection is the point where the concavity changes. So when you look at your first derivative, that gives a slope. If the first derivative is positive, my slope is, well, my function is increasing. If the derivative is negative, below the x-axis, my function is decreasing. If my derivative is positive, my function is increasing. But when you look at it, when you look at the graph, you can tell that it's decreasing here, and then it's no longer decreasing quite as much on this side until this point where it hits level, and then it starts increasing. So this point right here ends up being that point of inflection. And if we look at this, well, it'd be the point where my derivative was equal to 0. So, hey, that's where my second derivative equals 0. Now, a couple things that you need. You need my concavity to change. I can have the second derivative equals 0, but have no change in concavity. So what we need is, if it's underneath, the second derivative is underneath the x-axis, second derivative is negative, it's concave down. So f double prime of x is less than 0, it's concave down. If the second derivative is positive, it's concave up. So over here, this means it's concave down. The graph should open in this direction. Over here, it's concave up. The graph should open in this direction. And if you put those two together, you end up getting our original function. Now, it doesn't tell you about how high or low it should be. It doesn't tell you much other than the fact that you should have an inflection point over here. So the point of inflection is where the concavity changes. Now, the changes is very important because if you think about f of x equals x to the fourth, derivative is 4x cubed, and the second derivative is 12x squared, which equals 0 at 0, except x to the fourth, kind of like a parabola, a little bit steeper parabola. It doesn't change concavity. It's concave up the entire time. So if I was to look at the second derivative, what we do is just like we do with the first derivative test, we put any possible points of inflection on there, such as 0, and then we find the concavity on each side of it. Plug in -1, you're going to get a positive 12. Plug in +1, you're going to get a positive 12. Therefore, there is no change in concavity. There is no point of inflection for this graph. Oh, one other thing, anytime you do a number line, make sure you label your number line. Alright, so that brings us to the second derivative test. So we want to consider a function that is differentiable twice. So one of the big problems with the second derivative is you've got to be able to take the second derivative. If you get through the first derivative and you're running into a blank wall, or it's just getting out of hand, the second derivative could be pretty tricky to do. Sometimes it's very easy, very simple, and sometimes it's not so easy. But you do need to have a function that's differentiable twice, which does throw out absolute value graphs. We need to be able to take the derivative. We don't want it to be undefined. Okay. We also want to know what would happen if the first derivative equals 0 and the second derivative is positive. Okay, so let's think about what that is. Oop. First derivative is 0, so let's put C here. And the second derivative is positive. Okay, so what this means is it's horizontal, and this means it's concave up. Okay, so we got horizontal, concave up. Oh, that must mean C is a relative min. That's it. I mean, that is true. If you find that the derivative is equal to 0 and the second derivative is concave up, then you have a relative minimum. If the derivative was equal to 0 and it was concave down, you have a max. It's a relative. Now, the one thing that's a little bit of a pain is concave down. Down, I usually think minimum. However, when you draw a quick picture, you see that you have a relative max. I would suggest drawing a quick picture of that, and it might be just something like this. Okay, 0 concave up. Oh, min. 0 concave down. Oh, it's the max. Problems here. You have to take the second derivative, and it also can't deal with any of the corners. This is definitely a relative minimum, but if it's not differentiable, you can't do the second derivative test. But the nice thing about the second derivative test is this is really all you have to say. The first derivative equals 0, and the second derivative is positive, therefore you have a relative minimum. It's a very easy sentence to state. First derivative test, you have to say something about how the derivative changes from positive to negative at this point, therefore there is a relative maximum. Or the derivative changes from negative to positive at this point, therefore there's a relative minimum. That's a little bit of a trickier sentence to state. This, therefore you have a relative minimum, all you have to say. Alright, so let's try a quick second derivative test to find the relative extrema. So first thing you want to do, well, since we're dealing with h, you might want to find it. Find h prime of x, and you get 2x plus 3. And you want to know where it's equal to 0. So x equals -3 over 2. That's your critical point. That's where the derivative equals 0. I can't do where the derivative is undefined. I need it to equal 0. So that's our flat spot. Now all we have to do is find h, I'm going to say h and write f. Find h double prime of, well, probably want to start with x, which is just 2. And you're looking for h double prime of, well, -3/2, which is still 2. Now, I don't care what the number is, I care that it's positive. So therefore, it is flat and concave up. You have a relative min. So all you want to say is you have a relative min at x equals negative 3 halves, since h, since the derivative h prime of negative 3 halves equals 0, and h double prime of negative 3 halves is greater than 0. Don't say it's 2, say it's positive. That's what we want to have. We want it that's flat and it's positive, therefore it is a relative minimum. That's really it. So, 3 steps. Find your, I don't want to say critical values, because critical values are where the first derivative is equal to 0 or undefined. Find where your first derivative is equal to 0. And then 2, evaluate. So more along the lines of f prime of c equals 0. I keep on saying critical value. Some important value, some horizontal value. Evaluate f double prime of c greater than or less than 0. And 3, analyze. And conclude. So the devil's in the detail in this one. The fact that you have to find the second derivative, I mean, you can see where that's going here even in this next one. Find the first derivative, set it equals 0. Okay, not too bad. Don't forget your chain rule. Find the second derivative. That's the part where it gets a little bit tricky. Now, all else fails. Use the first derivative test. Now, sometimes you won't be able to even do this. They might give you an AP exam, they might give you a chart where it's like f prime of x and gives you all sorts of information, and then they give you a chart f double prime of x and give you all sorts of information, and you can't just do it directly. You might have to use a second derivative test. You might not even get a function. So here's an example where you would actually have to use a second derivative test, not the first derivative test. So all we know is the first derivative equals 0 for these points right here. And then we've got a graph for the second derivative. So I can't say whether I have a max or a min, and you could try drawing something out here, but all I know is it's horizontal at all of these points. So at negative 4, well, the graph is way down here. It's negative, and I know it could possibly have jumped up over here somewhere, but I have to assume it kind of keeps going. So negative 4, the second derivative is negative, so that means I'm flat and I'm concave down. Therefore, I have a max. Well, how about 0? Okay, well, it's flat, but am I concave up or down? I don't know. We cannot tell. And that's another big drawback from this. You have to have one of those two things. You have to know it's concave up or concave down. This has no concavity. It's kind of flat at that point. So I don't know whether it has a relative max, relative min there. How about here at 2? Well, it's negative, so it's concave down. So we have a relative max at 2. Over here at 5, way up here, well, it's positive, so it's concave up. So we have a min at 5. So that's how you can see this and not be able to do the first derivative test. I would have to either give you a picture or they give you a chart with information.